Bismillahirrahmanirrahim. Today I am going to discuss application of Schiff basis. As you have an idea, in my last lecture, I've explained the preparation synthesis of the Schiff basis. I've given you an overview what the Schiff bases are, and today I will give uh, applications Schiff basis with certain relevant examples, especially the applications of Schiff basis for the preparation of synthetic dyes. For the preparation of synthetic dyes, it will be a special emphasis on that. I will also explain some other applications as well. So before I start the discussion about the application, let me just give you a brief intro, a recall about the Schiff bases, what they are actually. Yesterday in my last lecture, that is about the chemistry of the Schiff bases, I told you whenever you see a bond, double bond in fact between carbon and nitrogen, and the nitrogen also carries some sort of substituent as well, this compound is supposed to be called as imine, as we have an idea about it. They are also called as azomethynes. Thirdly, they are called as Schiff bases, So compounds wherever you find a double bond between carbon and a nitrogen, whenever you find a sort of double bond between carbon and nitrogen, that compound is supposed to be considered as a Schiff base, We don't need to look around the substituents, whatever they are, what is their chemistry, aromatic, non-aromatic, aliphatic, whatever they are. What is the basic concept? The presence of the double bond between carbon and nitrogen that makes such compounds to be called as imine, azomethine, or Schiff bases, How the Schiff bases are produced, I've discussed those yesterday. Let me give you just a brief glimpse, As I will discuss, aldehydes and ketones, they undergo nucleophilic addition reactions. So nucleophile under acidic conditions could attack at this carbonyl carbon, giving negative nucleophile, and then this proton that from acid that can neutralize the presence of negative charge on oxygen, giving us corresponding alcohols. So whenever we start from aldehydes and ketones and react them with certain alcohol nucleophiles, in fact those nucleophiles undergo nucleophilic addition reactions. Nucleophilic addition reactions, giving us the corresponding alcohols. This is the general property of the aldehydes and ketones as they do undergo nucleophilic addition reactions. So one version of this reaction was, we have a different sort of nucleophiles. Somebody having a negative charge or somebody having lone pair of electron is supposed to act as a nucleophile, So similarly, we have an idea about the amines. Let's say we have some sort of an amine with R group. We have idea they do act as nucleophiles as well. So as far as the general reaction is concerned, that is supposed to be NH2, and this is how. Then in order to neutralize the positive charge, a negative charge on oxygen and positive charge on nitrogen, you know. One of the proton is removed from here. The same proton can get positioned with the oxygen, or proton from the oxygen can replace it, giving us the corresponding alcohol, you know. So we will get this one, we'll have NH and we will have R. So till this step, that's the same as I've discussed. A nucleophile gets attached with the carbonyl carbon through nucleophilic addition, gives us corresponding alcohol. But when our nucleophile is a sort of an amine, this reaction goes one extra step. What happens? This proton is removed from here to generate a double bond between carbon and nitrogen, kicking hydroxyl group out, and then both of these two bodies produce water as an eliminating species. So what happens? A double bond is generated between carbon and nitrogen. Here will be the R, the substituent with nitrogen, and this is the generation of a double bond between carbon and nitrogen. This is called as Schiff base. So as a conclusion, what could I say? Aldehydes and ketones, when they direct with amines, primary amines, they produce Schiff bases. Schiff bases means somebody having positive double bond between carbon and nitrogen. That is supposed to be Schiff base, you know. So this is one of the representative reaction which suggests the synthesis of a Schiff base by the reaction of aldehydes and ketones with amines, you know. So this is what is the basic about this synthesis. Once you synthesize, let's say, once you synthesize a double bonded, let's say, we have some substituents here as well. I can call it R1, R2, and this is the R3. Once you synthesize the Schiff bases, how you can use them? That will be called the application aspect, you know, how you can apply. We have an idea about the, let's say, Grignard reagents, where you do have your alkyl part in the form of negatives, mean as nucleophiles. So whenever there is a bond between nitrogen and carbon, and there is a negative charge on I should write the other way around, that will be more appropriate for you. Let's me write, there won't be no issue. RMGX, you know, the magnesium is supposed to be a metal. Metals are sort of electron deficient, so this bond between carbon and nitrogen, this is shifted towards this one, and it generates a bond between, what happens, we will have R2 and R1, here is your R3, we will have a bond with MgX. As the bond has been moved from the carbon to here, the carbon is supposed to lose the electron. Consequently, it will carry positive charge. In order to neutralize this positive charge, we have an idea these alkyl groups are supposed to be the negatives. Nucleophile, it will attack at the same at the carbon in order to neutralize its positive charge. So we will get something like that. That will be called as, we can call it R4, you know, 1, 2, 3, this could be called as R4. So at this point of time, you may put in acid or you may put in water, you know. So we will have nitrogen, we will have R3, this metal will be removed, proton will replace it, this will be R2, this will be the R1, also carry R4, you know, the one which came from the Grignard reagent, plus what we will have MgX along with OH, you know. So what has happened here? due to this reaction, we have increased the number of substituent of the and the carbon. We have increased the number of substituents on the carbon. So whenever you want to increase the substituent, want to introduce any substituent on Schiff basis, we can react them with Grignard reagents. So this is how you could do. You can increase the number of substituents. You can install substituents of your own choice, any aromatic substituents, aliphatic substituent, whatever is required, we can install. Some students do ask me that when we react aldehyde and ketones with Grignard reagents as well. So in this case, this negative R also reacts with the carbonyl carbon because it's a nucleophile. As I've told you, aldehyde ketone do react with the nucleophile. So let me write R1, R2, and then we have this one as an R3. So what happens then? Yes, we will have oxygen in the form of negative. Here is your R3, here is your R2, here is your R1. It is supposed to carry MgX at the first step, then we put in acids and waters, and then we neutralize this to corresponding alcohol R1, R3, and then R2. So some of the students do ask me a question that when we react aldehyde and ketones with Grignard reagent, we also increase the number of substituents, 3 substituents in the product. However, initially we have only 2 substituents. So this is how we can increase the number of substituents. Then why we want to generate the Schiff bases first from aldehyde and ketones. You got the question? Students consider that aldehyde ketones, when they react with Grignard reagents, the alkyl part from the Grignard do react at the carbonyl carbon, giving us the increase in the number of substituents, So if we can increase the number of substituents directly from the aldehyde ketone, then why we generate first imine and then we react them as well? Yes, if you want to generate only the number of substituents on the carbon, you can try this reaction directly with Grignard reagent. Okay. As I've told you, once we want to incorporate nitrogens into our compound as well, as I've told you, the presence of nitrogen gives compounds biological activities. They make them biopotent, They become biologically active. They become suitable for drug synthesis. They become valuable compounds for the preparation of drugs. So we want to increase the number of substituents at the carbon. We want to keep the nitrogen as well in the same molecule in order to induce drug-like properties, in order to induce bioactive features in that molecules. Then obviously we can introduce nitrogen through imine formation, means through Schiff base formation, and then we can go for the reaction with Grignard reagent to produce the corresponding compounds, where we will have a substituents as well, increase in the number of substituents, and also we will have the presence of nitrogen. So in the same compound, the substituents has been increased, one of extra substituent has come in, at the same time the compound also carries nitrogen. So there will be chance that you will get some lead molecules which have some potency, which can be biologically active. It's a separate story. What is biopotential? What are the biological activities? Just trying to make you give a view that compounds which carry nitrogens, they are supposed to be privileged for biological properties, So this is how you can do. So this is one of the aspect, one of the application of the Schiff bases, that the Schiff bases do carry the nitrogen, so that is why they are important for the preparation of biologically important molecules, Let me move on to the application of Schiff bases for the preparation of textile dyes, especially dyes, dye preparations. According to my previous lectures, what you have an idea about the dyes, especially the azo dyes, are the dyes which carry azo group. How we introduce azo group? Actually, we start off from some sort of amines. We go for diazotization. What is diazotization? What are the requirements of the condition? That has been very well discussed in a separate lecture, that is diazotization, and I've also given a separate lecture on azo dyes preparation. You may visit or consult that in order to get a bit more detailed idea. So we start off with certain amines, we go for diazotization, then we produce diazonium salts. We produce diazonium salts. Then we bring in certain couplers. Coupler means some sort of aromatic rings. We can bring those in, and as it has got the positive charge, mean it is an electrophile. We have an idea the benzenes do react with electrophiles and undergo electrophilic substitution reaction. So what could happen? I can write over here, So this is how the colorant is supposed to look like. As I've explained to you guys, it's a colorant. Due to the presence of an azo group, it is supposed to be colorant, but it can be it's an azo colorant. It can be converted into azo dye if we produce the salt, corresponding salt. We have an idea, the water soluble salts of the colorants are supposed to be the dyes. Let's say if we have an idea, it's a sort of a HD group. If we bring in some sort of a base like sodium hydroxide, so we can generate the corresponding salt over here. So as a result, this will be a dye. This will become a dye, an azo dye. This is an azo dye. Due to the presence of this group, the double bond between nitrogen linked to aromatic entities, especially that generates colors. These azo dyes have so many ecological issues, so many problems, toxicities for the environment. They are not eco-friendly. Azo dyes are not eco-friendly. Over the past few years, there has been a continuous opposition against the use of the azo dyes in textiles. Few of the countries have also banned many azo dyes due to their carcinogenic nature. So there has always been a demand for the preparation of alternative alternative to the azo dyes. So people come in with the dyes which do carry imine bond instead of azo bonds, mean they prepare dyes which carries as imine bonds, means they are in fact Schiff bases, mean they have generated this sort of, here is some sort of aromatic, any sort of coupler substituents are around. So presence of this Schiff moiety functionality has been introduced as an alternative functionality to the azode functionalities, and it has frequently been used for the preparation of azodides, for the preparation of non-azodides actually. How it has been done, I have to give you just a single example, people do have used, like let's say they have used salicylides, they bring in some sort of amines, some sort of an amines. As we have discussed before, the amines do react with aldehyde and ketones through nucleophilic addition reactions. So what has it happened? Sorry, it is supposed to look like this way. Here is your NH2 with the ring, supposed to carry positive charge. Here is the proton of the aldehydic part. Then one of the proton shifts from here to here in order to neutralize the charge, so we can get something like that. So what happens then? Finally, this nitrogen is supposed to carry one proton. So as per the discussions, it is an amine which has acted as a nucleophile. So amines do make double bond with the nitrogens, kicking hydroxyl out. So what should be then? Here is the presence of OH, the parent functionality. So what is supposed to be here? Is the carbon, here is the nitrogen, this is supposed to be the removal of water, and then this carbon carries one proton. This nitrogen carbon has a double bond. Here is the hydroxyl functionality that was present in the starting parent compound. Then what one could do, yes, it's a sort of an acidic moiety. You can bring in some sort of base and we can convert it into a salt, which is the basic requirement for the preparation of dyes. So we will get this sort of water soluble compound. In this compound, what is present? There is a present double bond between carbon and nitrogen, and the nitrogen carries one substituent as well. So as per the definition, as per our discussion, this will become an imine. Imine mean it is a Schiff base, Schiff base, azomethine functionality present between the two aromatic rings. As a whole, this structure will become some sort of a colorant, Again, the colorant has been converted into a water soluble salt, so it is supposed to act as a dye. It will become a colorant molecule. Water soluble colorants are called dyes, as it carries C double bond N. It does not carry N double bond N, so it will be non-azo dye, It is supposed to be a non-azo dye. So this is how people have used this is how the people have used, the aldehydes and ketones along with amines for the preparation of non-azo dyes. So this is one of the examples. Let me give you one more so that you can see how the dyes are produced. This is also one of the applications of the Schiff bases. It's a very much known, frequently used compound, the one with the 2 amine group, So we can do amines. What one could do, one could bring in salicylaldehyde. Two times we can bring in 2 moles of salicylaldehyde, we can have 2 moles of salicylaldehyde. So what can happen? One of the amine could react over here. The other amine number 2 could react over here. Following the same mechanism, same passion, and we could get this sort of the products, there will be a formation of an imine between these two entities, amine and aldehydic functionality. We will get an imine over there. The hydroxyl will remain the same. Similarly, this amine and this aldehyde will generate the corresponding imine. The hydroxyl I can write over here, I can over there, so no issue. It's remain the same. So this will be the product. Again, we have 2 sort of functional groups which are supposed to be acidic phenolics in nature. We can bring in 2 times 2 equivalents of sodium hydroxides, and we can generate corresponding salts. Okay, so once the salt is produced, we can use it as a coloring material, water soluble coloring material, then it will become a dye, and once it is used as a dye, prepared as a dye, it will be called as non-azo dye. So these are the 2 simple examples, very simple examples, which have given you idea that how the Schiff bases actually are being used as dye materials, and they are actually replacing the carcinogenic azo dyes. They are non-azo dyes and they are replacing azo dyes. So this is one of their application, this is one of their achievement. From the literature I've got 1 or 2 more examples which do explain, give an idea about their utility in azo dye synthesis, Let me give you an example which I got from the literature. This is one of the colorant molecule which has been used, have been prepared, and is an example of Schiff based dyes, Number 2 is this very much similar examples I've seen in the literature. Nothing has been changed. Just a single one of the carbon. There is this compound and this compound. The difference is just the presence of 1 extra carbon in this one. Let's say this body is A and this is B. The B carries 1 extra carbon. The rest is the same. So these are the dyes, compounds, colorants, Schiff colorants, I would say. Schiff based colorants actually being used One can imagine how they have been produced. As per my previous explanation to you guys, whenever you see a bond between carbon and nitrogen, you can simply break it off, and you can install the proton, you can install the nitrogen. So this will be the starting material and this will be the starting material, salicylaldehyde. As they are the same, so again, as per the retrosynthesis aspect, this will be the starting material and this will also be the starting material. Whenever you see a double bond between carbon and nitrogen, we just remove the double bond and we keep the double bond with carbon and install oxygen, and with nitrogen we put into protons, because we have an idea the aldehyde ketones reacts with amines and give us carbon double bond N. So whenever you see a double bond between carbon and nitrogen, we can make carbon the carbonyl compound and we can make nitrogen the amine. So we can get the corresponding reacting species. So this is how the Schiff bases are important for the preparation of dyes, especially textile materials. For the dyeing of the textile material, I'm trying to actually explain these things for the students who are interested to prepare non-azo dyes, because the azo dyes have some carcinogenic issues, toxicities, and their environmental related issues have reduced their utility, and most of the countries have put strict ban on their usage. So this is all about the applications of Schiff bases. I do hope you got the idea. You are supposed to follow the literature about the further applications of Schiff bases, especially in dyes and for the preparation of certain bioactive compounds, for the preparation of drugs. If you do have any questions, any issues related to today's topic, you may put your questions in commentary on YouTube, and I will try my best to respond at the earliest convenience, inshallah. So thank you very much for your time and patience, please. Assalamu alaikum.